Imagine being able to understand everything about the universe and solve all its mysteries by a computational approach that uses very simple rules. Instead of being limited to mathematical equations, using very basic computational rules, we might be able to figure out and describe everything in the universe, like what happened at the very beginning, what is energy, what's the nature of dark matter, is traveling faster than light possible, what is consciousness, is there free will, how can we unify different theories of physics into one ultimate theory of everything. This paradigm goes against the traditional notion that complexity in nature must arise from complicated origins. It claims that simplicity in fundamental rules can produce astonishing complexity in behavior. Entering the Wolfram's physics project, the computational universe. The core of Wolfram's framework is the idea that the universe operates like a massive computational system. So everything in nature is fundamentally computational. Computational means anything related to the use of computers, using algorithms, data processing, and mathematical models to solve problems. The universe and its fundamental laws emerge from simple computational rules. And those simple rules can generate highly complex behavior. Here's a simple example. We have 3 nodes with 2 connections. We'll define these terms in a bit. Now consider the following rule. Find 2 edges from the same node, delete one of those edges, and create a new edge from each of the 3 nodes to a new node. Here's the rule in operation. The simplicity of the rules contrasts with the complexity they produce, which could be the basis for the apparent complexity of physical laws. In Wolfram's framework, the entire universe is a hypergraph, made up of a vast network of evolving states. It's composed of nodes connected by edges. Nodes represent elementary atoms of space. The connections, or edges, represent relationships between these nodes. They can link more than 2 nodes at a time. A traditional graph connects pairs of nodes. A hypergraph allows complex multi-node relationships with an astonishingly large number of nodes, each node representing an atom of space. All physical processes can be described as computational updates on a hypergraph. Think about transmission of light. Instead of thinking of light traveling through a pre-existing space, imagine the hypergraph as the structure that is space. When light moves, it corresponds to updates in the hypergraph. Connections between nodes, representing points of space, are being updated according to computational rules. For example, a photon traveling from point A to point B corresponds to changes in the connections between nodes in the hypergraph. The speed of light emerges as a limit determined by the rate at which these updates can grow through the hypergraph. Thus, the movement of light isn't happening in space, but rather comes from the computational updates that define and evolve the hypergraph itself. As the hypergraph evolves based on simple rules, it creates the fabric of space-time. This process models space-time as emergent rather than fundamental. Just like water molecules forming a seemingly continuous fluid, space at a microscopic level is made up of discrete points. These points are not embedded in any pre-existing container, but they're connected in relationships that define space itself. Smooth and continuous nature of space is an illusion. at scales as small as 10 to the power of negative 100 meters, far smaller than the scale of subatomic particles like protons, which is around 10 to the power of negative 15 meters, the discrete nature of space becomes significant. In Wolfram's model, space is not a passive stage for matter and energy to occupy. Instead, it's the only fundamental entity. The hypergraph isn't sitting in space. It is a space, constructed and reshaped by the computational rules that govern the universe. Matter, energy, and particles are not independent objects within space, but are emergent features of the hypergraph itself. The dynamics of the hypergraph give rise to all observed phenomena, from particles to forces and interactions. If everything in the universe, matter, energy, and physical laws emerges from the properties of a hypergraph, then understanding space becomes the same as understanding the universe's fundamental nature. The evolution of the hypergraph is driven by rewriting rules, which dictates how connections change over time. These rules are assumed to operate at the smallest scales of reality, Planck scale, or maybe even smaller. The evolution of structures over time could correspond to the evolution of the universe. Every event or phenomenon, from subatomic particles to galaxies, is a result of a computational process. So space, in Wolfram's universe, is not just a passive container, but the active, evolving fabric of reality, with its discrete and dynamic nature shaping every aspect of the universe. The universe's complexity, including phenomena like space, time, and physical laws, might arise from the consequences of a fundamentally simple computational rule. This rule could operate at the most basic level, shaping the universe as we observe it. If such a program exists, the familiar characteristics of the universe, like 3D space, time, and the laws of physics, wouldn't be definitively encoded in the program. Instead, these features would emerge naturally from the rule's execution over time. The rule itself, if it exists, would be minimal and simple. The universe's rich structure would be a result of interactions and evolution dictated by this rule. This approach pushes for reconsidering what the raw material of the universe really is. Could it really be possible that such a small and elegant program is the architect of the vast complexity we see in the cosmos? If so, discovering and understanding this program would redefine our understanding of reality and provide the unified explanation for the diversity of phenomena in the universe. A key insight in Wolfram's work is the concept of computational irreducibility. Even though the rules are simple, their consequences may be unpredictable. In classical science, prediction often involves jumping ahead without simulating every intermediate step. For example, to predict the Earth's position in 1,000,000 years from now, we don't simulate every orbital step over that time. Instead, we use mathematical formulas derived from models like the two-body problem to compute the answer directly. This approach relies on the idea that a system's behavior can often be reduced to simpler calculations. It assumes we can be smarter than the system itself, using shortcuts to arrive at the outcome without following the full process. In Wolfram's computational framework, such predictive shortcuts are often impossible. Processes can't be simplified or predicted without performing every step of the computation. Computational irreducibility often prevents shortcuts in prediction. Even if we know the rules, the only way to see their outcomes could be simulating every step. Since we can't bypass the computational process, we must trace the system's evolution step by step to observe its behavior. This makes it computationally and conceptually challenging to test if a rule corresponds to our universe. If a system requires 500 steps to evolve, predicting its final state often necessitates performing comparable computational work, which involves simulating all 500 steps. We might understand the rules governing the first moments after the Big Bang, but calculating what happens billions of years later would require more steps than we could ever compute. While we might know the rules, we can't just simply jump ahead through the hypergraph and predict the universe's state billions of years into the future. We'd have to simulate every single step to see what happens, which can take an unimaginable amount of time. This means that no matter how smart you are or how powerful your computer is, you can't skip ahead. You just have to let the process play out. This no skipping steps rule is the hallmark of computational irreducibility. In essence, the universe computes itself, and the outcomes of many computations are undecidable or unpredictable, like the behavior of complex cellular automaton. A cellular automaton is a simple system made up of a grid of cells, where each cell can be in one of the few states, like on or off. The state of each cell changes over time based on a set of rules that consider the state of neighboring cells. Despite its simplicity, it can create complex patterns as the system evolves. Computational irreducibility provides a natural explanation for the apparent randomness and complexity in physical systems. It's impossible to know beforehand how many steps will be necessary to resolve whether the system stabilizes, evolves indefinitely, or dies out. A specific pattern, for example, might vanish after 3,000 steps. But there was no way to predict that beforehand without running all 3,000 steps. In some cases, determining the system's ultimate behavior might require an infinite number of steps, making the problem formally undecidable. This means there's no finite computation or formula that guarantees an answer in advance. A crucial concept in Wolfram's framework is causal invariance, which means different sequences of rule executions lead to the same outcome. Let's say you have three numbers, 1, 2, and 3, and you want to add them together. The order in which you group them doesn't matter. The final outcome will always be the same. Observers play an important role in understanding how the universe operates. They're embedded within the hypergraph and interact with it based on their localized perceptions. An observer is essentially a system that experiences the evolution of the universe. However, the concept of an observer is distinct from the usual idea of a conscious being. Observers here can be any system or structure that evolves within the universe. They are part of the computational processes and follow the same rules that govern the entire system. Observers emerge from the very rules that define the universe's evolution, and they interact with the universe through the rules. Now, in terms of causal invariance, the way an observer perceives events or outcomes depends on their position and the sequence of rule executions they experience. But the final outcome will always be the same for all observers, regardless of the specific path taken to reach that state. If two observers follow different sequences of rule applications, they might perceive events differently. But because of causal invariance, they will still reach the same final state. This means that even though the steps or the paths to reach an outcome might differ, the outcome itself remains unchanged. The actions or perceptions of observers don't disrupt the ultimate outcome, but are rather part of the process that leads to it. The causal invariance principle ensures that no matter the perspective or sequence of actions by observers, the universe ultimately behaves according to the same set of rules, and all observers, in their own frame of reference, will perceive the same fundamental outcome. Imagine flipping through the pages of a book. Whether you read it from start to finish, or skip around and read the chapters out of order, the overall story remains the same. Similarly, in Wolfram's work, no matter the order of events in the computational universe, the fundamental outcomes remain consistent across all perspectives. Over a century ago, computation was specialized, requiring separate machines for specific tasks. The concept of universal computation transformed this. It demonstrated that a single machine, given the right instructions, could perform any computation. This innovation became the foundation of modern computing, enabling general-purpose machines to perform diverse tasks through software. Wolfram applies this same concept to the understanding of the universe, extending it to the computational universe. He argues that computation isn't restricted to advanced devices like microprocessors. Almost any system capable of complex behavior, including simple ones like cellular automaton, can achieve universal computation. These basic systems process information and perform logical operations much like traditional computers. Wolfram demonstrates that even basic cellular automaton, starting from random conditions, can evolve into systems capable of universal computation. This principle, known as computational equivalence, supports the idea that universal computation is a fundamental property of systems, not just engineered machines. With the right knowledge and programming, any computational system, no matter how simple, can be made to perform complex tasks. This emphasizes the inherent versatility of computational systems, both in engineering and in nature. If the universe operates on computational rules, then nature itself might be capable of universal computation. If true, then the complexity we observe in the cosmos comes naturally from simple underlying rules. By studying the computational universe, simple programs that replicate the behavior of natural systems can be uncovered, and that would offer new perspectives on fundamental physics. In Wolfram's world, even the apparent three-dimensionality of space isn't a fundamental feature, but an emergent one. The concept of dimension in Wolfram's work emerges from the hypergraph's structure rather than being a fixed property of the universe. Dimension is an effective property determined by the way points in the hypergraph relate and connect to one another. On a microscopic level, space may deviate slightly from 3 dimensions or take an entirely different dimensional characteristics. Imagine a flat grid, like a chessboard. If you start in the middle and move outward, adding squares as you go, the space you cover grows in very regular way. This regular growth gives the grid its flat 2-dimensional nature. Now, think of a cube made of tiny blocks. As you expand outward in all directions, the space you're covering grows faster because you're moving through 3 dimensions. This is how we intuitively understand dimensions. How much space gets filled as you expand outward. In Wolfram's model, the universe isn't like a smooth grid or a solid cube. It's made up of countless tiny points connected to one another. like dots connected by strings in a massive spider web. The connections between points can be irregular. As a result, the way space expands when you move outward isn't perfectly neat. It's more like exploring a dense forest where the trees and paths are unevenly spread. The points and connections, the hypergraph as a whole that represents space, is constantly changing. To figure out its dimension, you would look at how the network grows as you explore it outward from a single point. So space dimensions are not fixed and can vary based on the underlying rules of the system. In different regions or at different scales, the effective dimension could change. It reflects how the hypergraph's structure grows under its rules rather than being predetermined. This approach contrasts with classical physics, where space is assumed to have a fixed dimension. While the hypergraph may have variable dimensions at the microscopic level, the universe seems to be three-dimensional at large scales. Just like the concept of dimension, space-time curvature emerges from how these connections behave at large scales. Imagine drawing a straight line on a flat sheet of paper. The line stays straight no matter how far you extend it. Now, imagine doing the same on the surface of a ball. Even though you think you're drawing a straight line, the line eventually curves because the surface itself is curved. This is what curvature means. It describes how space itself is shaped and whether straight paths, like light traveling in space, actually bend or twist. In Einstein's general theory of relativity, mass and energy bend space and create curvature. When light or objects move through this curved space, they follow what they think are straight paths. But because space is bent, their motion looks deflected. This deflection is what we perceive as gravity. As mentioned, space in Wolfram's framework isn't smooth. It's made of discrete atoms of space, connected within a hypergraph. When we zoom out and look at how these connections behave on a large scale, the hypergraph can take on shapes that resemble curved space. Just as water molecules, when observed collectively, behave like a smooth liquid, Wolfram's hypergraph behaves like smooth space at large scales. Remarkably, the equations that describe how this large-scale space behaves turn out to be Einstein's equations of general relativity. This means the same rules Einstein used to describe curved space and gravity naturally arise from the hypergraph in Wolfram's work. So the evolution of the hypergraph not only creates space, but also its curvature, which manifests as gravity. The concept of time is fundamentally redefined in Wolfram's framework. Instead of being an independent universal flow, time emerges from the ongoing process of computation within the hypergraph that defines the universe. Time progresses through the continuous updating or rewriting of the hypergraph that represents space, and the rules govern how parts of the hypergraph are rewritten. This ongoing rewriting process happens everywhere in the universe, and it's this progression that we perceive as the flow of time. The rewriting process itself is the fundamental driver of time, with no external mechanism governing it. Since Einstein's breakthroughs in the early 1900s, space and time have been considered interconnected within a single fabric, space-time. Now, how does Wolfram's model, which treats space and time differently, align with this? In Wolfram's framework, space is the structure of the hypergraph, while time is the process of its computation. These are distinct but interconnected. Observers are embedded within the universe. They are part of the hypergraph. As embedded entities, observers perceive time through the relationships between computational events, not as an external dimension. This perception depends on causal relationships, how one event leads to or depends on another. Each rewriting of the hypergraph is an updating event. These events define the causal structure of the universe. An event can't occur until all its required inputs, outputs from prior events, are available. This creates a partial ordering of events based on causality. The result is a causal graph that represents the relationships between all events. Observers experience time through this causal graph. They can only perceive updates when they themselves are affected by an event. This means their knowledge of the universe is limited to the causal chain that reaches them. So time isn't a pre-existing backdrop and not a fundamental continuum, but an emergent feature of the universe's computational rules. It emerges from the sequence of rule usage. The perception of time and causality is shaped by an observer's position in the causal network. Events that haven't causally influenced the observer remain invisible to them until the causal chain reaches them. Time may differ for different observers depending on their position and interactions within the causal graph. This echoes Einstein's theory of relativity and its concept of time dilation, but arises from computational relationships rather than geometric spacetime. The universe evolves and the hypergraph changes constantly. These changes are like little updates in the connections between points in the web. Energy in this model is essentially a measure of how much activity or updating is happening in the network over time. Every time one event in the universe affects another, it creates a link in a causal graph. These links represent how events influence each other and, collectively, the amount of influence or activity determines the energy present in the system. Imagine a city's road network. Cars represent the activity or motion within the network. Roads connecting intersections represent causal relationships, how one event leads to another. The more cars are in the streets, the more energy is present in the system. In Wolfram's model, the hypergraph is like this road network, and the energy is the amount of traffic flowing through the connections. Energy isn't something separate from space-time. It's an intrinsic property of the network itself. The flow of activity through the hypergraph determines how much energy is present at any given point. The same activity in the hypergraph that defines energy also produces the space curvature, linking energy and gravity. Instead of treating energy and spacetime as separate concepts, Wolfram's model unifies them as different features of the same network. Imagine a giant dance floor when dancers represent points in space and their movements represent activity in the hypergraph. The more complex and fast-paced the choreography or activity, the more energy is present. The connections between dancers or causal edges in the hypergraph define how the dance progresses, creating a flow of influence across the floor. The dance floor in this analogy is the hypergraph, and the choreography reflects the energy and its impact on the system. Quantum mechanics has a reputation for being strange and counterintuitive, but Wolfram's model provides a unique way of understanding it. In classical physics, things are predictable and straightforward. If you throw a ball, it follows one definite path. Every action leads to one specific outcome based on the forces acting on it. Quantum mechanics turns this idea upside down. Instead of one definite path, The ball simultaneously explores all possible paths. What we observe is not a single outcome, but a range of probabilities for where the ball might end up. In Wolfram's model, quantum mechanics isn't something extra that needs to be added. It naturally emerges from how the universe works at its most fundamental level. The hypergraph web evolves over time through a set of rules and updating the nodes. The rules for updating the hypergraph can often be applied in different ways. As the hypergraph updates, it creates a branching structure, a multi-way graph. Each branch represents a different way the universe could evolve, corresponding to different quantum possibilities. So the hypergraph's evolution follows not just one path, but multiple paths simultaneously. These paths represent all possible configurations of the universe's state. Observers experience specific outcomes due to branchial space, a conceptual space that organizes branches of the multi-way system. In our everyday understanding of the universe, the speed of light is a universal speed limit, 186,000 miles per second. This limit comes from the structure of space-time itself. It's not just about how fast something moves, but how reality is built. In Wolfram's model, light moves through a hypergraph, but its speed is determined by how information spreads within the structure of the hypergraph. Imagine trying to leap ahead in this network faster than the rules of the hypergraph allow. It's not just about moving fast, it's about finding a way to bypass the inherent structure of space-time itself. Imagine a room filled with gas molecules bouncing around randomly. If you wanted one molecule to travel from one side of the room to the other at incredible speed, you'd need to perfectly bounce off other molecules in just the right way. This is similar to what faster than light travel would require in Wolfram's model. You'd need to figure out how to navigate through the complex web of the hypergraph, bypassing the usual constraints. In traditional physics, the speed of light is treated as a fixed law. In Wolfram's framework, breaking this limit is more like solving an engineering puzzle. It's about figuring out how to manipulate the hypergraph in ways that theoretically allows for faster spread of information or motion. The odds of achieving this is comparable to getting all the gas molecules in a room to line up perfectly and drive a single molecule across the room. It's theoretically possible, but practically speaking, it's almost impossible due to the complexity of the system. As mentioned in Computational irreducibility section, computational rules evolve the hypergraph over time. These rules are so complex that they're computationally irreducible, meaning you can't skip ahead to see what happens. You have to compute every step. For faster than light travel, you would need to somehow shortcut this irreducibility, which is incredibly challenging. Wolfram's model suggests that faster than light travel isn't strictly forbidden. It could happen if you could manipulate the hypergraph in exactly the right way. This might involve finding rare and precise configurations that allow for shortcuts through the network of space-time. Imagine you're in a giant maze with walls that changes as you move. Normally, it takes time to navigate the maze step by step. Faster than light travel would be like finding a way to instantly jump to the exit without following the usual pathways. While this might be possible in theory, it would require incredible precision and understanding of mazes' structure, something that might be practically impossible. In Wolfram's work, Dark matter, a mysterious and invisible component that makes up a significant portion of the universe's mass, is hypothesized to be an emergent property of the microscopic structure of space. The unseen influence attributed to dark matter, like its gravitational effects on galaxies and cosmic structures, could arise from the way space-time is fundamentally configured at its smallest scales. This hypothesis shifts the understanding of dark matter from being a distinct, standalone entity to the property embedded in the very fabric of the universe. If true, it would reveal that dark matter was hiding in plain sight as an overlooked or underappreciated consequence of spacetime's fundamental behavior. Understanding dark matter would require identifying specific features or patterns in the hypergraph that correspond to its observed gravitational effects. The difficulty is in bridging the abstract mathematical structures of Wolfram's models with the empirical observations of dark matter in the universe. If dark matter is indeed a feature of spacetime itself, it would fundamentally alter how cosmologists approach the study of the universe's structure and evolution. While Wolfram's theory is ambitious and innovative, it faces several critiques. The framework must align with and extend well-established theories like quantum field theory and the standard model of particle physics. The hypergraph model must make specific testable predictions that can be empirically verified. These predictions need to be clearly distinct from those made by existing theories, like quantum mechanics or general relativity, so that they offer new insights and avenues for experimentation. Testable predictions could involve specific behaviors or phenomena that arise from the evolution of the hypergraph model, like new forms of particle interactions, gravitational effects, or other observable phenomena that differ from those predicted by conventional physics. For instance, Wolfram's model might propose new insights into the nature of dark energy, the repulsive force that expands the universe. These predictions must be verifiable through experiments, observations, or simulations that allow comparison with data from real-world experiments or astronomical observations. While Wolfram proposes that a simple rule governs the universe, identifying this rule has proven to be a challenging task. The complexity of the universe, with its vast array of phenomena, from the smallest quantum particles to the largest cosmological structures, makes it difficult to pinpoint a single, simple rule that accounts for everything. The behavior of systems in nature is influenced by countless variables and interactions, which can result in outcomes that are highly sensitive to initial conditions and evolve in ways that are not always predictable. Wolfram's simple rule must not only account for the vast range of phenomena observed in nature, but also be consistent with existing theories like quantum mechanics and general relativity. The difficulty in finding this rule comes from the fact that even though the rule itself may be simple, the emergent complexity that arises from its application can be incredibly complex and unpredictable. The quest to identify this rule remains a central and ongoing endeavor in his work, as it has the potential to radically shift our understanding of reality itself. Wolfram's theory isn't positioned as a competitor to other established approaches in physics, like string theory. Instead, Wolfram envisions these theories as potentially compatible components within the broader framework of his models. The framework seems compatible with many existing ones like string theory, an influential and widely studied framework, and many developments in mathematical physics that seem to plug into the models. String theory might represent a specific case or corner of Wolfram's models. While this remains speculative, Wolfram is optimistic about compatibility. The models in the framework are not built in opposition to these theories, but rather they provide a new foundational layer that could contextualize and extend them. The debate isn't about one model replacing another, but about uncovering how different models relate to and inform each other. String theory and similar approaches might emerge as special cases of Wolfram's broader computational framework, just like how different mathematical tools are suited to different aspects of the same problem. Wolfram's openness to integration suggests that his work could act as a meta-framework for physics, incorporating insights from diverse, well-established theories. By identifying commonalities between his computational models and other mathematical approaches, Wolfram aims to bridge divides in theoretical physics, promoting collaboration rather than competition. If successful, this integrative approach could provide a clear path toward the unified theory of physics. Wolfram's approach to a theory of everything starts with a bold idea. There's a single, simple rule, a tiny program that could explain everything about the universe. But the search for such a rule is still ongoing. Imagine you could describe the entire universe, every star, every particle, every physical law using one tiny set of instructions. It's like finding a super simple recipe that, when followed, creates everything: galaxies, atoms, and the behavior of light and gravity. In Wolfram's model, this recipe would be a rule that governs how the universe evolves step by step, starting from an incredibly basic structure. People working with this framework have found many interesting rules that explain certain pieces of physics, but they haven't found the ultimate rule that explains everything at once. For example, one rule might explain how particles behave, but it doesn't account for the shape of space. Another rule might describe space well, but doesn't include particles. The goal is to find one perfect rule that covers all these aspects in a unified way. If we do find this ultimate rule, an interesting question comes up. Why would our universe, with all its complexity, comes into being from something so simple? Imagine writing down a single, short sentence, and that sentence somehow describes every book, movie, and idea that has ever existed. It feels strange that such richness could come from something so simple. If we find a simple rule that generates the entire universe, it might seem almost too good to be true. Why would we, out of all possible universes, live in one that is so elegant and easy to describe? Think of the universe as a vast Lego world. You might assume it takes thousands of different types of Lego pieces to create something so detailed and expensive. But what if it turned out you only needed one type of brick and a single, simple instruction to create everything? Even if we never find this ultimate rule, Wolfram's work suggests that it exists within the space of possible rules. The challenge is, of course, finding that rule, like searching for a needle in an infinite haystack. If our universe really is described by a simple rule, maybe we should feel incredibly lucky to exist in a universe that's so elegant. In Wolfram's framework, consciousness is viewed as an emergent phenomenon resulting from the underlying computational processes that govern the universe. Consciousness in this model is not a separate, fundamental force like gravity or electromagnetism. It arises naturally as a byproduct of the immense complexity and self-organization inherent in the computational fabric of reality. Conscious beings are deeply embedded within these computational processes. Their experience of reality can be viewed as an interaction with the ongoing unfolding of the universe's computations. This means that what we perceive as awareness or selfhood is tied to how we process and interpret the computational rules and patterns governing our existence. Consciousness could emerge wherever sufficient computational complexity exists. Biological or artificial systems that reach a certain level of complexity might give rise to consciousness. If the same fundamental rules that create stars and galaxies also give rise to subjective experience, then Wolfram's work is a unifying framework for understanding both the material and mental aspects of existence. This could open new avenues for exploring consciousness through computational and physical models, potentially reshaping how we study and define the mind. The universe is fundamentally deterministic in Wolfram's model. The randomness we observe emerges from our inability to compute every detail. Everything that happens, from the birth of stars to human consciousness, follows from the initial conditions of the system. This shows that free will could be an illusion. If everything is determined by computational rules, then every thought, decision, and action may already be set in motion by the initial conditions of the universe. Computational irreducibility blurs the line between determinism and unpredictability. Strangely, irreducibility is not just a limitation. It's what makes the universe dynamic and unpredictable. If everything were reducible, life would be boring. You'd know exactly how everything would turn out, and there would be no surprises. Like if you already knew how your life would unfold, you wouldn't need to live it. You'd already know the answer. Irreducibility means the passage of time isn't just an illusion. It's the process of the universe computing itself. Every moment is like a step in a grand cosmic calculation that can't be skipped or shortcut. If life were computationally reducible, you could skip ahead and know exactly where you'll end up, what jobs you'll have, who you'll meet, and so on. But because of computational irreducibility, you can't skip ahead. You have to live each day, making decisions and seeing how things unfold. This unpredictability, while sometimes frustrating, is also what makes life worth experiencing. If the universe is a grand computation, on one hand, this could make the universe seem purposeless, as everything is determined by the same rules, and nothing is truly random. On the other hand, one could argue that purpose emerges from the inherent complexity and self-organization of the system. Systems governed by simple rules can naturally organize themselves into structured and coherent patterns without external guidance. This self-organization can mimic what we perceive as purpose or direction. While the rules themselves may lack inherent goal or purpose, the complexity and organization arising from their interactions can give the appearance of purpose. This could manifest as the formation of galaxies, life, and consciousness, all outcomes of underlying computational rules. In computers, machine code is the lowest level language that tells the hardware what to do. It's the foundational layer beneath all the complex programs and interfaces we interact with. Now, Wolfram's idea is that the universe has its own machine code, a simple underlying structure that produces all the complexities we see in physics. We don't know all the specific instructions in the universe's machine code yet, but we have a good idea of its overall structure. In other words, we know the broad framework, even if we're still figuring out the finer details. For centuries, different branches of physics, like quantum mechanics, general relativity, and particle physics, have seemed disconnected. Each branch has its own beautiful mathematical descriptions, but they often feel like separate puzzles. Wolfram's model acts as a Rosetta Stone for physics. The Rosetta Stone was an ancient artifact that helped scholars decode Egyptian hieroglyphs by computing them to languages they already understood. In the same way, Wolfram's model provides a framework for understanding how different areas of physics, no matter how complex or distinct they seem, are connected. It shows that these pieces of physics are all idealized versions of what's happening at the most fundamental level. Imagine you're assembling a massive jigsaw puzzle, but each piece comes from a different set. Quantum mechanics might be one set, general relativity another, and so on. At first, it's hard to see how they fit together. But Wolfram's model is like finding a guide that explains how these separate puzzle pieces come from the same big picture. Gravity, quantum mechanics, and other forces are unified in this hypergraph-based model, with the specific rules of evolution encoding a theory of everything. Wolfram aims to unify the physical laws that describe microscopic, quantum, and macroscopic, cosmological scale universe through the same computational framework. For centuries, physics has been divided into different areas, each with its own rules. If Wolfram's ideas are correct, they could unify these areas, showing how they all emerge from the same machine code. The universe is incredibly complex, but Wolfram's model suggests it all stems from something simple and elegant. The beautiful mathematics used in physics might not just describe the universe, they might emerge naturally from the underlying rules of Wolfram's machine code. Traditionally, black holes are considered a feature of spacetime, arising from the extreme curvature predicted by general relativity. In Wolfram's framework, black holes are emergent features of the underlying structure of space itself. Even what we perceive as matter might, in some cases, be a manifestation of spacetime's structural properties. Both black holes and particles are persistent structures in spacetime, maintaining their form over time. General relativity traditionally considers black holes as regions of spacetime and generally associated with macroscopic or large-scale objects, while particles are thought to be quantum entities, governed by the principles of quantum mechanics. In Wolfram's work, this distinction is less rigid. Features of spacetime can exist in any scale, from the microscopic, like electrons, to macroscopic, like black holes. Particles and black holes might share a common origin as emergent phenomena of spacetime, differing primarily in scale and the forces acting on them. Matter, including particles and black holes, might be reinterpreted as configurations of spacetime, blurring the lines between traditional categories of objects in physics. The sharp division between macroscopic and microscopic phenomena becomes less meaningful in Wolfram's model, as all structures are manifestations of the same fundamental processes. By treating black holes and particles as similar structures, Wolfram's approach could bridge the gap between general relativity, the macroscopic world, and quantum mechanics, the microscopic realm. This reimagination of spacetime features like black holes and particles highlights the unifying potential of Wolfram's theory of everything. Traditional physics has struggled with paradoxes that pops up at the interaction of general relativity and quantum mechanics, like black hole information paradox. General relativity or classical physics say that information falling into a black hole is lost when the black hole dies. But according to quantum mechanics, information can't be lost. How can quantum information be preserved when a black hole evaporates? In Wolfram's framework, such paradoxes begin to dissolve. By modeling the universe through discrete computational rules, phenomena that once seemed contradictory now seem as natural consequences of different perspectives on the same underlying structure. Just as astronomers explore the cosmos with telescopes, we can examine the computational landscape to uncover new principles of nature. The behavior of many simple computational rules is shockingly complex, defying the intuition that complexity asks for sophisticated origins. This insight reveals a fundamental fact. Nature's complexity arises not from complex starting conditions, but from the inherent richness of simple computational processes. By solving the technical challenges that restricted earlier physicists, Wolfram's framework offers a way to make discrete space a viable and foundational concept. Accepting space as discrete fundamentally alters how physicists view the fabric of the universe. A discrete model of space could bridge gaps between quantum mechanics and general relativity, as it naturally aligns with the discrete phenomena observed in quantum scales. If Wolfram's models prove correct, they would validate the early instincts of physics pioneers, who suspected the discreteness of space but lacked the tools to prove it. Wolfram's work on a fundamental theory of physics suggests that the universe operates like a computer. At its core, this cosmic computer has a kind of machine code, a basic set of rules or instructions that govern everything. The search for a single rule to describe the universe is like looking for a hidden treasure. If we find it, it could reshape how we understand reality itself. But whether or not we succeed, the journey helps us explore the question of why our universe is the way it is, and whether its elegance is the result of sheer luck or something deeper. What seems simple at the foundational level may, through iteration and interaction, brings the complexity of the universe we experience today. The notion of a simple program at the core of reality emphasizes a big shift. Instead of seeing the universe as built upon layers of complexity, we might find that simplicity lies at its core, with all complexity emerging naturally from it. Even if we don't find the ultimate rule, searching for it helps us better understand the rules that govern smaller parts of the universe, like particles or space. Wolfram's approach is arguably better described as a formalism than a specific, predictive theory of physics, a framework or system of rules that focuses on the mathematical or symbolic representation of phenomena, hence enabling precise descriptions and calculations. It serves as a framework upon which specific theories can be built or tested. A theory in physics usually involves specific assumptions about the nature of reality, like particles, forces, or fields, make testable predictions, and explain observed phenomena. Wolfram's work is identified as formalism, focusing on structure and logic rather than meaning or interpretation. Wolfram's framework, as formalism, proposes rules for constructing spacetime and generating physical laws, but doesn't claim to comprehensively describe or predict all aspects of reality. It provides a computational platform upon which various specific theories like quantum mechanics or general relativity might be developed or unified. It focuses on how the universe's complexity might be generated from foundational computational rules rather than prescribing a fixed set of equations or entities. Rather than being a final theory of everything, it offers a dynamic framework to explore how simple computational principles can lead to the diversity of physical phenomena. Wolfram's model is a glimpse into the software running the universe. While there's still much to discover, the idea that we can decode the machine code of reality is very exciting. It promises to not only to unify different fields of physics, but also deepen our understanding of why the universe behaves like the way it does, transforming beautiful but disconnected ideas into a single, coherent story. Nature leverages the fact that even very simple computational rules can produce extraordinary complex behavior. This principle is at the heart of how natural processes generate complexity without requiring extensive engineering. In human engineering, we design systems to be predictable and controlled. By contrast, nature thrives on systems where simple rules generate rich, emergent complexity. The computational nature of the universe explains how simplicity can generate the complexity we see in natural phenomena. Many paradoxes and mysteries in science begin to make sense within this framework. While engineering systems are designed to be predictable, Wolfram's approach embraces the unpredictability and complexity that emerge from simple rules. This unpredictability, rather than being a limitation, is fundamental to nature's ability to create. If the universe operates as a vast computational process, it opens up the possibility that humans could eventually develop technologies that mimic and harness these computational rules. This might lead to advances in fields like quantum computing and artificial intelligence, where computational systems are modeled after the universe's own processes. Given that the universe itself is computational, it's conceivable that we might one day be able to simulate the entire universe using powerful computers and make breakthroughs in understanding the true nature of reality. By modeling reality as a hypergraph and leveraging principles of computational irreducibility, Wolfram offers a novel and unifying perspective on space-time and physical laws. Shows that our universe is fundamentally a computation in progress.